Okay, so if folks can navigate back to the GitHub page, so the URL is up here. This intro to DAS repo on Eileen's page, and select the forge.ipynb file. Then they should be able to open the file in Colab just like previous by selecting this button here. And this I think we just kind of learned a little bit about how to navigate Google Colab and how to troubleshoot at the same time. This tutorial, we're going to spend about 20 minutes. We're going to spend about 20 minutes here looking at some data from the Forge project. So that's a US DOE project. And to start, let's just scroll down. It's going to take a little bit to get the data, hopefully. So please run this first cell. And if you click this files button on the side, you should see these begin to kind of populate through. So I'm just going to take a second to make sure that there is actually success with this, just because we had the issue before. So you should just be able to run this cell. What this cell is doing is, again, downloading GDown, the Google Drive access point library, HelpSpy to do some data processing. And then we're going to get a library called Forge Utils, and there's a zip of a couple of Forge files. And hopefully people can confirm that they can get that data.
Looks like we've got some good positive responses so far.
Slowing down a bit. Okay, great. So these files are a little bit smaller. If you just, so while that downloads, hopefully for everyone, so the Forge project is basically a vertical vertical DAS. It's 1,000 meters vertical in Utah. And the goal of the experiment was to monitor a geothermal microseismic experiment, basically an injection for geothermal stimulation, enhanced geothermal system. If you'd like to read more about the Forge project, you can visit the University of Utah site or the DOE Forge site, or read the phase 2C has just wrapped up in the last year. And so you could read about what the results of the DAS recording and also Geophone comparison are here from the geothermal repository. So the data set is an available data set, and actually the data are linked through these scripts here, which are hosted. The data are all hosted from Utah. So if you click on one of these links, this is the Silixa IDAS data. What this is just a script of wget is a kind of a bash protocol to bash function to grab files. So these are 15-second files. You can see the timestamp here. So this would be one DAS recording for 15 seconds on April 19th, 2019, UTC time. And so that's day, hour, minute, second, SegWi format. And so all I've done here is I've kind of written a little script in this Forge utils package to basically just, based on some time range, find the data sets there and downloaded them. And I've preloaded the data set here so that we don't crash the Utah servers when everyone tries and downloads the data set. And if people have been successful here in, let me check the chat one more time to make sure that people seem like they're not having too many issues, so that's good. So if everyone, when you get these data, hopefully that they've downloaded already, you can run the second cell. And so now we're going to get going. Basically, we have those two scripts from Utah. So get all Silixa would be this one, all the Silixa data. There's also another script here called get all SLB, that'd be Schlumberger. So they recorded the Geophone data, also SegWi format. So each of these is a Geophone file from the Geophone array that was in the well. And these scripts are available if you would like to, after the workshop, after this period, kind of go on your own and access the whole data set. But for now, all I've done is I've put 4 Geophone and 4 DAS files into this Forge data folder, right? So this is pre-filtered workshop data that we can look at. And then we also have this utilities library. Okay, so enough about that. Let's look at something more interesting. So we run this cell here, and that's going to bring in the Forge utils package and HelpSpy. And then I just wanted to show you that if you run this cell, this is how easy kind of interacting in this environment can be. So we are going to import a couple of these libraries, set up some parameters like gauge length, the spacing between channels, the units in nanostrain per second, so it's a strain rate unit of DAS, and something about the, a couple other parameters, set a time, and then it's going to download, basically it's going to find the paths, those URL wget lines, and download them from Utah. Now I've put this script switch workshop here to block us to just use the local data. So this is switch is where you'd kind of take the training wheels off to look at the whole data set. So you could scale up this later to look at a whole different time range if you're interested in looking at an earthquake or something. We're then going to read these files with some parameters. So we're going to read the DAS files with the DX and a couple of other parameters. Then we're going to read the Geophone data. And then we've loaded that into a stream, and then we're just going to plot it with this, this function here. So this is going to plot a raster plot, or what I call an image plot, or Eileen called it a raster plot, in the background. And in the foreground, these wiggles on top are the geophones. So just to orient here, the color scale in the background is the DAS data. The color scale is in strain rate, in nanostrain per second, between 6 and -6. And the time is along the y-axis from 0 to 0.4 of a second, and then the distance in the wellhead is here. So we're 300 meters depth to a kilometer in depth. And what you're seeing is an earthquake, a micro earthquake. It's actually a double event. So there's a P wave here, and then some S energy. Then there's a second P wave here, and some more S energy here. And you're just gonna have to take my word for it that this is a double event. We've looked at this. Actually, colleague Ariel Lelouch has looked at this more. He's in the chat and on Slack if you're interested in talking with him more about this. But the point here is that you can see that this DAS data, this has been bandpassed between, I think, 10 and 150 hertz. The main arrival here between the Geophone and the DAS is really consistent in terms of its energy. So it was just this easy to get going. So I think that this should be kind of clear that you could modify this, but let's kind of look at what all we have here in terms of this utils package to kind of begin to look at either other portions of the Forge data set or or other data sets completely. So focusing on downloading the data set first, we could, one way to use this would be to, based on this event time, right, that I've set up. So you could define a dictionary in Python that would be based on an event. So like event 0 or event 1. And then you could go to Iris Wilbur 3 and find earthquakes that occurred during the time of Forge. I put the time in the header of this notebook, but it's around April 2019. So if there was a teleseismic earthquake, for example, that occurred in Fiji, then you would take that time, propagate it to Utah, and then look for that time. You could set up an event to look for that time of the Forge data set. So that'd be kind of interesting. Like I said, I've prepackaged just the first event here. So just looking at this 0th event. What we're doing is we're going to get the paths for DAS from those wgets. Then we're going to download them. So I'm just printing out what exactly is being done here. We based on some start and end time, we find the timestamp. Then we just find this line in that script. then we download it we actually run this command on the inside of Google Colab, and it pulls the data into Google Colab or onto your local machine if you have it set up there. And the same thing works for the Geophone data. So this is how the script would work to download data. This type of this kind of protocol, I'll say, like this type of way to access data with these wget lines is maybe you're more familiar with Iris to kind of query for data. This is a more rudimentary way to access data, but it's quite efficient when the data are being stored locally. So there's many different types of data, and this has already come out kind of in thinking about the Brady Hot Springs. We're really going to be talking about SegY data today, but there are other formats. And so SegY is going to store all the data for a certain time range, like 15 seconds, all the channels of that data set. And you're going to have to read all of that data in order to look at any one channel. So let's start by QA/QC is going to be the next section to look at some of these data. And I think that the goal of this next section should be to kind of look through basically how you would bring in data from the field. Or let's say someone handed you some data, or you go out to these available data sets and pull some data. And now you have 10 terabytes of information, or you have 2 terabytes of information. What is the first thing that you do with that data set? I think we should really start with kind of understanding that the first thing to do is really to make sure you have everything populated in the correct way, because there's not a standard way to do this yet for DAS. You can see that by the DAS data formats are on all these random, different ways to store data. So you might get some data that might be in a TDMS format without headers populated. So if you're to take a look at one of these files, this DAS data set, for example, this is going to be a SegY file. So reading it in, we have 15 seconds of data, but we have traces. I'm just plotting the first 15 traces here. If you look at any one of these traces with the HelpSpy kind of tools that are at our disposal with the kind of, so DAS is a stream, and a stream is a collection of traces. And in SegY, we can read in this DAS stream and then look at the 15th trace. So that would be like the 15th channel of a DAS array then. You'll note that when we plot these stats, none of the information has been populated. It's all in the SegY header. And so to populate that, we need to go through and actually add these information from the SegY into the station and location. But we're also missing some parameters here, like the gauge length, for example, is not in the standard SegY header. The channel spacing is not populated. The units of this are nanostrain per second. So these kind of information need to be kind of added to the metadata. So that's kind of our task one. Task two is to actually establish where we are in space, right? So this is from the report. Silixa made this diagram. This is called a channel map, would be the term that I would use. So from the instrument, the box is here. We're told distance along the fiber is equals 0 at this point. And there's E2000 connections. So these would be like the splice points that come into the instrument. Then there's a loop of coil, 100 feet. That would be the fiber. It has many fibers in it. It's just a cable. And then there's a patch panel, a splice panel that splits out the fibers here in this diagram. And so one of these fibers then goes to the wellhead. So this would be the ground surface, so the wellhead level. And we're told that at that point, this single mode fiber, for example, is at 135.47 feet of the cable length. And then if we look at this fiber runs down to the bottom of the well. And we're told there that the fiber distance, if this is the wellhead, was kind of datumed to 135.47 feet or 41.29 meters. And we're told that the wellhead ending is 1,037 meters, 0.8 meters. So what do we do with this type of information? This is probably developed by tapping on the wellhead and then finding where this location was in the data set. But regardless of how this was found, this kind of tap test information that comes in from the field, we should really only think about distances between 2 points, these key location points. This is a good distance to use. So we can see that this is 996.51 meters of continuous running fiber between 2 points. You know, there's extra fiber in the instrument, for example. There might be extra fiber at the end of the well, but as long as we know these two key locations and the relative distance between them, that's all we need. So kind of establishing that you know, fiber optic distance in the well is all we really need. So if we run these parameters, we can do the same thing. The Geophone information is available from the Utah website, so we'll just load that in too. And then we'll populate the SegWi headers. So this just takes the DAS stream and that DX, and then based on the channel incrementing, basically finds where it populates the stats side of the DAS traces. So you can see that the 15th channel now is a DAS station of 15, and we have you know, we're told that this is exactly this distance, and we kind of also put in the channel Z there. Okay, so I'm just going to run the next couple of cells to populate headers, read files, and this kind of thing. So there's some kind of basic methods here that I've included in this library utils, Forge utils. So this read function, for example, if you pass it the DAS units at the start, when you read in the data, then you'll get all these things automatically, including the units here, which is good to kind of just be able to track this metadata down, keep it with you. Okay, so I've included at this point in the notebook a quick restart function. So if everything before this point in this notebook, let's say you just got back from lunch or something and just showed up to the notebook, you could just run this cell, and this is going to set up everything that we need so far to be able to proceed with the notebook. So we're going to download everything, we're going to read in everything. We've set up the parameters that we just took a look at, and then we've added them in for this time range here. So if you wanted to just start from here, you could. So let's take a look at how to use that tap test information. So I'm going to plot the image again of the DAS data set for this example earthquake. So here we're plotting every channel as a column here, right? So this is an image plot where every channel is a different column, and we're just looking at that half second when the earthquake was arriving. The nanostrain go from -200 to 200, and we can actually, we put some yellow lines here that are separated by the distance in the well. So we found out from the tap test this is about a 996 meters or something. And so this would be a way to kind of interactively see that this yellow line and this yellow line here, this is not the kind of portion in the well, right? It would make more sense if this starts here. I've just started this arbitrarily at 50, but if you move this around, you'll see that you can actually, you can actually establish kind of just intuitively where this starting channel is based on the relative distance inside the well. And the issue comes in terms of the precision of where you could actually draw this, right? So if I change my bounds here to be not from 0 to 1.3 kilometers, but just around 200 where the wellhead, where you kind of think the wellhead might be with this first yellow line, like from 0.15 to 0.25, let's say, kilometers is the XLM here. You can see that, so now we're zoomed in right around the wellhead, right? Before the wellhead is a lot of noise, and in the well, it's quieter. And so that's why I'm making that determination. You can see that right here, we're kind of, we have the gauge length, which is 10 meters, but we have our channel increment, which is 1 meter. So we could move this maybe a few meters back in one direction, from 200 to 198 or something. But you're still within a gauge length, right? So moving this, you can see that moved the yellow line from there to there. But the gauge length is still 10 meters, right? So this would be 20 meters. So the gauge length is still like 5 meters this side, 5 meters this side. So there's a certain amount of resolution that you actually have when you're doing tap tests. And that's why oftentimes when you're actually recording a tap test survey, you'll try and ramp up the channel spacing to make it as fine as possible to look at these spacings. But so that seems pretty good. So we're going to say the first channel is at 194. And if we go out to the end of this array, we'll see that the other the other yellow line is down here at 3. Right, so we're kind of in the noise here, maybe at the end of the well, but we have the kind of correct location of this down here at the bottom too. So this is kind of a way to kind of begin to QA/QC the data set. Is kind of an important piece, is this tap test, establishing the geometry. And for those of you who have done this, you'll know that this is can be an excruciating task to actually make a determination about where you are in space, especially when you're doing this with a telecom array where you have limited information. So the last piece of this is just going to be the plotting. So I wanted to kind of just show to the attendees who aren't really familiar with looking at these images, for example. This is the DAS data set in kind of maybe a more conventional way of plotting individual traces as wiggles. So time is moving up the y-axis, space is moving along the x-axis, and each trace here, each channel, is spaced apart by 20 meters. So you can see that same earthquake there, right? Double P, P, P. But if we actually have with DAS, we actually have this skip parameter I've included to kind of be able to move, to skip a certain number of channels in the stream. So we put the stream there and we put the skip. We actually see that the density is too large for a wiggle plot when we actually move it to its full resolution, which is, for geophones, for the 12 geophones, it's easy because they're separated by a pretty large increment. But moving, the DAS data set should maybe be better, more easily plotted as an image like this. So here, plotting these same wiggles as just positive and negative values on a color scale allows us to then use a skip of 1, and we can see much more clearly the full resolution of this array. So if we move this color, the C-lim variable parameter kind of controls the color bar clip here, which is then it becomes an important parameter for image plotting. So here you can see, you can actually begin to see those S waves there. So this is, and again, like if you were, kind of looking at the resolution of what a geophone array might be, like a 30-meter spaced geophone array, you might look at something like this. But the DAS data set is much more finely sampled. So, and then you can do this kind of overlays where geophones are going to be in wiggles above the DAS. So that's more clear a little bit, I think, to plot these data sets together. Okay, so we're going to take 5 minutes, I think, and actually we have 15 minutes. Maybe Eileen or Kasey can correct me on that, but we have 15 minutes. I think I'd just say, let's go into breakout groups now, and we can kind of think about these questions together in smaller groups.